Hey GIS enthusiasts! Welcome back to another ArcGIS Pro tutorial. In this video, we learn how to delineate watersheds in ArcGIS Pro using digital elevation models, DEM. This technique is essential for hydrological modeling, flood risk analysis, and water resource management. We'll cover preparing DEM data, filling sinks and calculating flow direction, creating stream networks, extracting watershed boundaries. If you love GIS, hydrology, and remote sensing, hit like, subscribe, and turn on notifications because more ArcGIS Pro, GIS programming, and Python tutorials are on the way.
A watershed is a land area that drains water into a specific body of water. Okay, so if you see here, so this area, right? So this area will be a watershed area, because why? All the water that is falling over this area is, or the water that fall, or any of the precipitation that is falling on this land, piece of land will be accumulated in a single point, right? So this point could be called as a pour point. So all the water that is falling to this area is accumulated to a single point of body. Okay, so these areas can be called as a watershed. So similarly, there will be another watershed beside this watershed, right? So all the water precipitation that is falling over those area will be accumulated into another pour point. So these kind of areas are called watersheds. Okay, so whether it be, so all these, so these watershed will be, the boundary will be at the highest points, right? So if you see here, it's all the peaks here because the water that is falling on this peak will either flow to this side or to this side, right? So all the water that is falling over these sides will be accumulated into streams and then finally they are accumulated into a pour point. So for this pour point, this is the watershed area, right? So if you are taking this water body as a pour point, this area is its watershed. Okay, so these kind of areas are called watershed. And in today's exercise, we will see how we can actually delineate these kinds of watershed from our satellite imagery. Okay, so for doing this analysis, the data that we'll need is a DEM data. Okay, so do you guys know what is DEM? Yes, so like for normal imagery, all those pixels will be representing the reflected radiance, right? So whatever the case of DEM data, what kind of data would the DEM be like expressing, right? So DEM data is actually having the elevation data. So so if you see the analysis, we need this elevation to actually find out the watershed, right? So for doing a watershed analysis, this will be the methodology that we'll be following. Okay, so we'll have either of these DEM data. So it could be SRTM DEM or Astro DEM or Cartosat DEM. Okay, so if we have any of the DEM data, this will be the methodology that we'll be following to find out our watershed or delineate our watershed so that we can do further analysis on that. Okay, so the first step we'll be doing is doing a fill sync, right? And next we'll be doing the flow direction. And next we'll be doing flow accumulation. And using the data, we'll be doing applying some threshold and we'll be extracting the drainage. Okay. To this drainage, we'll be identifying a pour point, and then using this pour point, we'll be delineating a watershed for that pour point. Okay. So this is the methodology that we'll be following. Okay. And so before that, we'll need to acquire the DEM data. Okay. Okay. So we'll be acquiring our DEM data from this website. Okay. So that is as a Earth data search. Okay. So if we go in here, first we'll need to, so like as we did for the USGS Earth Explorer, we'll need to first log in. Okay. So in here, I have already logged in. Okay. So if you want to log in first, or you have to register an account, right? So for that, you can just search for NASA Earth data login. Okay. So it will be creating us, or it will be giving you a separate web page where you will need to log in or register account. Okay. So just follow whatever the steps that are given in here so that you could register your account. Okay. So click on register. to whatever that is given there, you can just follow and then create an account. After creating account, you can just go over to Google, search for Earth data search, okay, and then come here. So after you are logged in, this will be your view, okay. So for which area you want to actually download the data, you can just pan your map over to that area, and then maybe you can just uh, go a folder, okay. So I'll be finding data for my this area, okay. And next I'll be downloading my Astro DEM, okay. So search for Astro DEM in here. So you'll be getting Astro Global Digital Elevation Model V03. Click on that one, and then it will give you the datasets that's falling over your region, okay. So I have these two tiles. You know what? I'll just download this tile, and the file that I want is DEM data, right? So Astro VO3, I have dem.tif. So I'll be downloading the TIFF data. Okay. So that is downloading. Okay. So like I told you, the first thing that we'll need to do is do field sync. Okay. So why do we need to do the field sync? So what are sinks? So we can say that every imagery will have some kind of errors, right? So sinks or peaks are errors due to resolution of data or rounding of elevation of the nearest integer value. Okay. So those are the actual errors. Okay. So sinks should be filled to ensure proper delineation of basins and streams. So if the sinks are not filled, derived drainage network may be discontinuous. Okay. So this is an example of a sink. Okay. So the data should have gone like this, but because some kind of error on the satellite sensor, there's a false depth here, right? So it should have been on the same level as this slope, right? So these slope are like continuously decreasing slope, this one. But then there's a irregular channel for one single pixel. So which means that it's actually a error in our data. Okay. So when there are errors like this, we might not be able to get actual accurate basins or streams because this depth will be taken falsely as a depth of the data elevation, but this is not actually a depth. This is some kind of error because of the satellite sensor. Okay, so when there are these kinds of error pixels, we need to first clear this. Okay, so that is why we are doing the fill sync. So what is the fill sync do? The fill tool uses equivalent of several tools such as to locate and fill sync. So what does it do? It locates and fills the sinks. So what does it do? So if there is a false sinks like this, it will actually fill the sinks. So that is what, or that is why we are doing the fill sinks. Okay. So the tool iterates until all sinks within the specified area are filled. Okay. And then it can also be used to remove peaks. So remove peaks are something like this, like so if the slope has should have been gone like this, but instead of like a peak or like the depth in here, it has actually created a false peak. So that means there is no peak like this on that pixel. So if this is like depth of like 10, 15, 5 something, but this should be have been like 25. So which means that this is actually an error. So it should have been on the same slope as the other pixels. So these things also can be used to can be corrected by doing the fill sinks too. Okay. So first we are doing the fill sync so that these error pixels are corrected. Okay. So that is why we are doing the fill sinks. So next what we'll do is we'll find out the flow direction. So flow direction is something like if we have, okay, so we have the slopes, right? So if we find out we have every slope. So the flow direction, what it does is first it actually find out how much slope your land has, and then whenever the water falls on it, or wherever the flow direction is actually used to find out in which direction your slope is facing. Okay, so you have different peaks and everything. So this is used to find out in which direction your slope is facing. Okay, in ArcGIS we are using this in a D8 model. Okay, so D8 model uses this kind of signals to actually find out or represent in which direction your uh, slope is facing. Okay, so if it's east, if it's one, right? So if there is, so this model, like you can see this model, right? So this model is called the D8 or 8 direction 4-point model. Okay. So if there is a value 1, which means that that peak is facing to the direction of east. Okay. If it is 2, the peak is or the slope is facing the direction of southeast. If it's 4, the slope is facing south, and if it's 8, it's southwest. If it's 16, it is like west. If it's 32, it's northwest, and 64, it's north, and it's 128, it means northeast. Okay, so these numbers will be used to represent in which direction, right? Because this algorithm cannot process your text, because everything can be, it should be done by numbers, right? So the directions will be represented by these numbers. So if it's 1, it's to the east. If it's 16, it's to the west, and if it's 64, it's to the north, and if it's 4, it's to the south. Okay, so these numbers, so these are the 8 numbers. This is a D8 4-point direction model. So 1 to 128. So these numbers will be used to represent in which direction our slope is facing. Okay, so why do we do that? So we have fill things, and then we are finding out in which direction each of our slopes are facing. So why we do that? So that we can find out the flow accumulation. So what is flow accumulation? From the DEM data, we can find out in which or in wherever the waters will uh, accumulate, right? So we'll be doing, we have the filled DEM data here. So for example, this DEM elevation will be a filled data. Okay. From this, we'll be finding out the flow direction, right? So flow direction is in the sense in which direction the slope is facing, and when water like falls on it, in which direction the water will be flowing, right? So that is the flow direction. Okay. So these directions, right? So these are the directions. So these directions will cannot be processed by ArcGIS. That's why we use the D8 model. So if you see here, we have, so if you take the pixel, this 14 pixel, okay. So if you see the surrounding pixels, you know that water cannot flow from a lower elevation to higher elevation. It will only flow from the higher elevation to lower elevation. Okay. So if you see the 14 here, okay, so that means that, so all these are pixel values of elevation. So when water falls on this specific pixel or this, this specific point on the ground, it cannot fall to the highest elevation. So we have all other pixels are highest elevation. So the only way that it can flow is either to this direction. So this direction will be our southwest, right? Southwest. So it will be represented by 8. Okay, so that is represented by 8. So if it's flowing over here, so it could only flow in 3 directions. It could only flow from this direction, or this direction. But we know that water will be falling towards a higher slope or a steeper slope, right? So if you see here, the elevation here is 14 and the elevation here is 12. So water will be flowing downwards, right, to the south. So that's the direction here, right? Similarly, we are creating the flow direction for every one of our pixel values, right? So it will be finding out flow direction for every one of the pixel values, right? And this data will be represented by a DA direction model. So if it's like this, it will be represented by number 2, right? So if it's like this, it will be represented by number 4. Is it direction like this? It will be represented by number 8. Okay. So that is how the flow direction will be done. Okay. So after flow direction will be done, then we can find out the flow accumulation, right? So flow accumulation means where the water will be accumulating or where channels will be created, right? So if you see the pixel here, right? So the water that falls on this area will be flowing down to this area, even this area will be flowing down to this area, this area will be flowing down to this area, right? So all these points will be demand. So if all these points are weightage 1, then this flowing will be found to will be flowing a weightage of 4. Okay, so all these points will bring the weightage of 4 here, and then from there the water falls down, right? So in here also it will be going like that. So we have all these points that it forms the accumulation of 8. So wherever these numbers are accumulating, that's the place where streams will be formed. So that will be the flow pattern. Okay. So if we have the flow accumulation, then we can actually create the flow pattern. Okay. So that flow pattern will be found out by using our threshold. We are applying the threshold and we will be extracting the drainage, right? So if we have the flow accumulation data, then we can find out where these drainages are, and then we'll be able to find out the streams, and then finally, by following this methodology, we'll be able to find out our watershed or delineate our watersheds. Okay. So this is the methodology and this is the process for determining the flow direction, flow accumulation and the flow pattern. Okay. So for that, first we'll be going into a ArcGIS, right? So we'll need to add our DEM data here. So I'll be using this data to find out our watersheds. Okay. So the first method that we'll need to do is the fill sync, right? So if you go to methodology, the first thing that we'll need to do is fill sync. But before that, we have to find out in which projection our data is. So if you go here, it's versional WGS 984, but then I'll have to first reproject this into our projection of UTM zone. I'll have to reproject into a projected coordinate system. So I'll be setting up my project raster. Okay. And in here I'll give my input raster of this image and output raster, that will be that name itself of my output coordinate system will be WGS 1984 UTM zone 43 node. Okay, and I'll just run this. Okay, so I have my projected DEM data here. So this DEM data I'll be inputting to my fill sinks. Okay, so if you go to tools, so I'll go to toolboxes and spatial analyst here. And in hydrology, I'll have all the tools that I need to do the watershed. Okay, so I have the fill, the flow direction, flow accumulation. So everything I have in here. Okay, so first I'll be doing the fills. So my input raster will be my projected data. Okay, so maybe I'll just remove the first one. Okay, so this will be my projected data and output. That will be that name itself. So it will be doing all the fill operation. So iteration phase is completed and it's completed now. Yeah, it's not showing any kind of changes, but there could be, right? So there could be some kind of changes that has happened, and the highest and lowest values are the same. Okay, so after we have done the fill, so we'll just follow the methodology. Okay, so we'll first fill the things, then we'll do the flow direction, the flow accumulation, and we'll set the threshold to find out the drainage. And using this drainage, we'll be uh, identifying a power point, and using that power point will be delineating the watersheds. Okay, the
Okay.
numbers like you'll understand when you do the
Okay, sir.
flow direction. Okay, so after we're done, so we did the projection because it was in a geographic coordinate system and we converted it into a projective coordinate system. So we did the project raster. After that one, we use the projected DEM data to do the fill. Okay, so after we are done the fill, we'll be doing the flow direction. So in here itself, we will have the flow direction. So click on flow direction. The input image will be our filled data. Okay. So we are setting the filled image, and then output, let it be that itself. And this is the DA direction model. Okay. So the direction model, we have different direction models, but the most commonly used is this DA direction model. That DA direction model was what I just explained here. Okay. This is the D8 direction model. Now if you run that, you will understand now. So I'll just run this, and it will be creating a flow direction raster image. Okay. Okay. So now this is the output of our flow direction. Okay. Now if you see the symbology here, you can see the numbers 1 to 128 here. Okay. Which means that the peaks here, right? So we have this peak here. So if you see this direction, that is a 64, right? So what does 64 mean? Which means that those slopes are facing the direction of north. Okay. And this blue, it means that it's 4, right? So if you see our chart, it means that those slopes are facing the direction of south. Okay. So what does it mean? So when water flows on this area, then so since those are facing the south direction, the water will be flowing towards the south direction. Okay. So that's what this means. Each of the using a digital elevation model, it is creating, it is taking the pixel values and finding out in which direction the water will flow, right? So this way. So this direction, right? So this image is same as this image. But since ArcGIS cannot display these arrows, it's displaying these numbers, right? So you'll be using these numbers, or which numbers? These numbers, right? So 1 to 28 numbers to display the same data that is, or the same kind of thing that is shown here, right? So it should be displaying in which direction these slopes are facing, and when water falls on it, in which direction the water will be flowing. Okay, so that is the thing that is represented by this flow direction. Flow accumulation is done, flow direction is done, we'll be running the flow accumulation. Okay, so using this direction model, this tool will be trying to find out where the waters will be accumulated and where channels will be formed. Okay, now if you see here, it's asking for input flow direction raster, and I'm inputting my flow direction image here. Okay, so flow one, that one, next two. Okay, so that is done, and the input flow direction is DA, output water is flow, and we'll just run this two so that we'll get the flow accumulation image of where the channels will be formed. So we've done the flow direction, the flow accumulation. This will be
Either it will take based on the flow direction or
the flow direction, because using this data, this
like
1 to
like it
28
will
data.
it will check the connectivity also.
Yes,
Why?
so
Because every streamline should have the connectivity, right, sir?
yeah, so it's
So
like
it will
this.
check
So
the even
it
the
will be,
connectivity also, right?
yeah, yeah, it will be checking all the pixels and finding out where these data will be flowing. So it will be like this.
Hmm.
It will be doing the same operation. So wherever these pixels flow or show it directed towards a single pixel, it means that's where the water will be accumulated, right? So all these things it will do it will be using this. So basically we are using the elevation, right? So we are using the elevation to find out where the water will flow and where the water will accumulate. So that's what this flow accumulation raster does. So it will be using the flow direction diagram to find out where water will be accumulated and where channels will be formed based on the elevation data.
Okay, sir, got it.
Now, if you see here, it should have displayed my data here. Okay, but now you can see it's all dark. Okay, so I think it's a bug of ArcGIS in this version, because if you go to symbology, okay, and if you set the classify option, you can see it failed to display the raster as classified. Okay, that is because this one, this like the statistic hasn't been correctly made. Okay, so if it's showing the same for you guys, what you can do is you can just remember the name. Okay, the name is flock12. Okay, now remove the data from my content and go to a catalog and find out where this image is created, right? So it should have created in my Watershed uh, database, and this is the data flock12. Okay, so right click this data and then you can click on the calculate statistics. Okay, so it means that since it didn't show anything there because it failed to calculate the statistics, so we'll be manually calculating the statistics for the image. Just click on run. Okay, so if that is done, it will be added to a map, and now you can see a main river. Okay, so if you just you can see, so this is where the water has been accumulated, or where the main river is flowing. So you can see how the water, how it shows the main river is flowing. But then we need to find, and we don't need just the this main river, we need all the streams, right? So to do that, you can either to visualize that, you can go to a symbology. Okay, and give the symbology as classified, and we'll be having two classes. Okay, so we need classes of where water is and where there is no water. So for that I'll set the this as black, and then I'll set the water bodies as white. And now you can see the upper value and lower value. So 0 to this amount, so this accumulated amount only it shows the black, and then less than this amount it's showing this white amount. Okay, so I can give a random amount. Okay, so you can just give whatever amount. So if I'm giving 15,000 here, okay, now I'm able to visualize most of the streams. Okay, so most of where the water is accumulated. Okay, so if you don't want this value, you can also change it. So if you give 30,000, let's see, now I can visualize most streams in here. Okay, so this is just a symbology. Okay, now from this I need to create a layer having only the streams data. Okay, so I don't want this data where there are no streams accumulated. I want only the data, or I want an actual layer where only these pixels, or where the water is accumulated. I only want this one. Okay, to do that we can use our raster calculator. Okay, so if you are geoprocessing tool, we'll just set our raster calculator. We have used raster calculator before, right? Do you guys remember where we used our raster calculator before?
Calculate the NDVI.
Yeah, for calculating NDVI, right? So that is where we are setting up the equations on a raster image. Okay. So my equation will be over where what I need to extract from here is the flow accumulation raster, where it has the value pixel value greater than 30,000. So 30,000, 30,000. So
So what we have given before, like to visualize the
yeah,
streamlines,
yeah.
so that value only we have to give here, right?
Yes, yes. So if you are okay with the visualization that you have got, then you are creating an actual
Hmm.
layer from that visualized data. So in this
Okay.
data, both streams and the actual ground is there. But we need only the streams from this data. For that, we'll be doing a raster calculator and applying this amount. So only the pixels that have value greater than 30,000 will be created here. So that is the condition that I've given.
Okay, sir.
From the flow accumulated data, pixels having value greater than 30,000 will be given to my new layer. Okay, so the name I gave is flow accumulation 30. Okay, so now that has been created. Now maybe we can change the symbology of that data. So it has two classes, right? So 0 is where there are no value, and 1 is where I have the streams. So now I have the streams created. This is my stream data. Okay, now using this data, so all these are rasters, right? So I need to, so if I want these as, so these are line actually. So waters are actually represented as line data. So if you want to convert this to a feature, I have a tool in my geoprocessing tool, in the hydrology tool, that is called stream to feature. Okay, so this thing can take up the streams from my data, and then it will be creating a vector feature. So what does it do? It converts a raster representing a linear network to features representing the linear network. So it takes up the streams in this data, and it will be creating a vector class of my streams. Okay, I hope you guys getting it, right? Because this is raster data. I want actual vector data of the streams from this form.
Yes, sir. Yes,
Yeah.
we understand.
So that's why I'm giving my data here, and it'll also, so it's asking for input the stream raster. So stream raster is the image that I created from my raster calculator, and then the flow direction. So I'll also need to input my flow direction, which is this one. Okay, and stream, maybe I can just give stream vector info. So I have the stream vectors, and I'll just run this. No. So before running the stream feature, you'll need to find out the stream order. Okay. So in here we have the streams in here. So before we do the stream feature, we'll need to find out the stream order. So do you guys know what is stream order?
Yeah, from the highest elevations to lowest elevation, it should go.
Yeah. It's something like so. So we have different streams here, right? So maybe- so it's something like so. When two smaller streams forms. So the smaller streams are ranked from 1 to whatever number, right? So when two similar stream forms to form one stream, it's a second order stream. Okay, so we have two first order streams. Two first order streams forms to form a second order stream. And a second order stream and a first order stream will be still a second order stream. Okay, but if there's a second order stream, so this is a first order, this is a first order. So when two second order streams forms to form a like joins, it forms a third order stream. Okay, so it is like something like one and it forms the second order string, and then second order string and second order string will be forming a third order string, and third order string and third order string will form a fourth order string, right? But then first order and second order will still be second order. Second order and third order will still be a third order, right? So this is a stream order. So we'll be finding out this stream order from my image so that I can find out which is the bigger streams and what is the order of these streams. Okay. So for doing that, I'll be doing my stream order. So input stream raster will be my this, and then input flow direction, I'll be giving my flow direction, and I'll give my stream order. Okay, and we'll just run this. So that thing that I gave, that is called the triangular stream order. Okay, so what I just explained, that is called triangular stream order. So if you see here, we only have three order streams in here. So okay, so you see here, so these two streams are first order stream. So these two first order stream joins to form a second order stream, okay, and then we have here two first order stream joins to form a second order, and a second order and first order stream joins to form still a second order stream. A second order and first order stream joins to form still a second order stream. But then we have two second order streams here which joins to form a third order stream. And even though there's a first order stream joining to a third order, it's still third order. So all the way over here, it was still a third order stream. Okay, so this is the stream order, and then this stream order data will be converting to my stream to feature. Okay, so I'll just click on stream to feature. I'll give my stream order data. Input flow direction will be my flow direction, and I will give the stream vector in here. Okay, now I'll just run this, and it has now created my stream data. Okay, now if I go to my symbology, I can set the unique values and I can get the grid code. Okay, so grid code is actually the stream order of these streams. Maybe we can, so let it be. The second one we can just give a color. Okay, so this is the stream order. We have two different streams that are formed. And we'll just enable this one so it's easy to visualize. Okay, so this is the stream order. Okay, so after we have created the stream order, next what we'll need to find out is, so if we come over our methodology, now we have filled this in for the four direction flow accumulation. We set the threshold. So I will set the threshold as 30,000. Okay, and then we got our drainage, and we did got our drainage, and we also created our stream order and then converted into the vector data. Okay, now what I'll need to do is I need to find out my pour point. Okay, so what is pour point? So pour point is where, so so for this watershed, this is the pour point, right? So all the water that is accumulated to this area. So that is the pour point. Similarly, we'll have to find out a pour point. So if we come over this area, okay. So if I am checking, or if I am setting this as a pour point, then watershed will be created like this. Okay, so all this water is accumulated to this pour point, right? So a watershed will be created like this. So if I am setting as this data, then watershed will be created like this. Okay, so the pour point is where the water finally gets accumulated. So if I am setting the pour point as this stream, then it will be creating a watershed of all the area that accumulates to the formation of this stream. Okay, so that is the pour point. Okay, so now to set a pour point, you will need to create a feature class. Okay, so we'll have to go to our catalog. So you will have to, I have already a pour point created. So what you need to do is you will have to go to your catalog, right? You need to create a new feature class. Okay, you'll have to create an empty feature class, set the same projection as your data. Okay, so it is a projected UTM zone 43 data, so you'll have to set a feature class of the same data, then you'll go to edit. Okay, create. So the data, it will be in point. Okay, so you'll be creating a point feature class. So and then using the point feature class, we will be creating a pour point. Okay, now if you see over here, so if you see over here, I already have a pour point generated. Just a minute, guys. എന്ത് എന്ത് ആ ഞാൻ വരാം. ഓ അരയായല്ലേ, ഇതൊരു 10 15 കൂടെ ഉണ്ടാവും. ഏ ആണോ? Okay, okay. ഞാൻ വിളിക്കാം. Yeah, sorry guys. So where were we? Yeah, so we need to find out a pour point. Okay, so we need to identify to which point to which point we are trying to find out the data. Okay, so if you see over here, I think I already had created a pour point. So zoom to layer. What is this one do? So if you see over here, so what I did was, okay, well, I created a empty feature class, okay, and then I went to my editing toolbar, and then I created a point over this area. Okay, you can see. So this area. So I will be finding out the watershed that is uh, providing or that is supporting to the formation of this stream. Okay, so this stream. So all this area will be counted as a watershed for me. Okay, so I have identified the pour point and I set the pour point here. Okay. So what I do, I created a new feature class and I created a point. So I just take the feature class and then place the point here. Okay. So to this watershed or to this pour point, I'll be creating my watershed. Okay. So to do that, what you'll need to do is, so after you have created your pour point, you'll just have to save your data. Okay. Now what you'll do is, if you come over to a tools, okay, so if you come over to tools, you'll have the watershed. Okay. So we have the tool that is called watershed. Okay, click on the watershed. It will be asking some input features. Okay, so it will be asking for input D8 flow direction raster. So my flow direction image was flowed there, this one. Okay, okay, and then it's asking for the feature pour point data. So the pour point is my feature class that I point feature class that I created, and I created a pour point in here. Okay, and I'll just be creating my watershed now. Now if I click on run here, see, now you can see that a watershed has been created. Okay, so for this area, the watershed has been created. Okay, so still you have to understand that this thing is a raster data, right? So this is a raster data, but I want my watershed region to be in a vector format. Okay, so to convert that, you can just use the tool. Let me see which was the raster to vector. The tool name was, okay, it's raster to polygon. Okay, so if you see over here, if I select raster to polygon, okay, so I have the tool here, raster to polygon. So I'll be creating this raster watershed region to a polygon feature class. So the input raster is the watershed, and yeah, and then I'll just run this. So this raster has been converted into a vector feature class. Okay, now we have my vector watershed area and I have the streams. Okay, now I can just clip the stream, right? So I'll just use the clip tool to actually clip my data. So I have the streams vector and I have my watershed. Now I can just clip this, and now I have my, sorry, okay, so I have my watershed and I have my streams created. Okay, so this is how you actually delineate your watershed regions.